and this is lecture 32. So in the previous lecture we were discussing a differential amplifier with a current mirror load, right? So we started discussion on this structure, and we found out that the short circuit current of this structure was double that of a structure which doesn't have a current mirror load, right? The one that has a resistive load. Let's say we kept it at VCM, right? So we saw that the short circuit current, that the incremental current that was flowing was the total current that was flowing through this branch was I naught over 2 plus Gm times delta V over 2. This is I naught, and this current was flowing through this transistor, was getting mirrored through this transistor, and this becomes I naught over 2 plus Gm delta V over 2. However, this current here was I naught over 2 minus Gm delta V over 2, which means the difference current, that is Gm times delta V, was flowing into the incremental short circuit, right? In this case I have put a battery just to be mindful of the fact that we are dealing with quiescent conditions also, right? So this is different from the case. This was different from the case where we didn't have the current mirror. Right? So if this was VCM plus delta V by 2, and this were VCM minus delta V over 2, and we did something similar. So this current still would have been I naught over 2 plus Gm delta V over 2, and this current would still have been I naught over 2 minus Gm delta V over 2. However, note that there is no mirroring that is happening from the top, right? Since there is no mirroring that is happening from the top, the short circuit current, right? So assuming that, okay, so I shouldn't have put VCM there, because the value of battery that I should put in this case should have been what? If this is RD, this is RD. This battery value should have been VDD minus I naught by 2 times RD, because that's what the quiescent value is, right? Right? So we hold it at quiescent value. If we hold it at quiescent value, then this current is always I naught by 2, right? So the difference current that would have flown, right? So difference current that would have flown out of the difference current that would have essentially flown out of your out of the VCM, right, out of the battery, would have been Gm delta V over 2. That is half the amount, right? Oh, sorry, I mean it should not be out, it should be in, right, the other direction, because the current from top is higher, right? So the excess current should flow in this direction. The excess current would have been Gm delta V over 2, right? So as you can see that by simply putting a current mirror in the circuit in the left, right, we are able to essentially double the short circuit current. Okay, so if I have to find out the Norton equivalent of a differential amplifier with a current mirror load, then what does the Norton equivalent look like now? The Norton equivalent essentially looks like this. So this is Gm times delta V, and this is some R out. We haven't yet figured out what this R out is. So this is something we will do next. So this is diff-amp with current mirror load. Okay. And what was the condition for the diff-amp without current mirror load? Or we can simply say diff-amp with resistive load. So this was short circuit current was Gm delta V over 2, and the output resistance was Rd parallel twice Rds. Correct? So if you recall, we did this why the output resistance looking down is twice Rds, right? Okay, so this is for diff-amp with resistive load, or without current mirror load. Okay, okay, fine. So that is as far as the short circuit current is concerned. Let's now investigate what will be the effect of output resistance, right? Okay, so in order to figure out output resistance, what should I do? Incrementally, what should we do? We are talking about incremental output resistances. Incrementally, we should short the inputs, correct? So this current source also goes off. This guy also gets shorted, right? So this is M1, M2, M3, M4. Again, we are assuming M1 is exactly equal to M2 and M3 is exactly equal to M4. Okay, okay, fine. And this is an incremental picture. Again, let us be mindful of the fact that this is an incremental picture and not the picture where we are having all the biases, all the quiescent points in place, right? Okay, so what we are essentially trying to figure out, that if we apply a test voltage V test, right? So what will be the incremental I test flowing in? That's all essentially what we are trying to figure out, right? And naturally, if I neglect channel length modulation, what is incremental I test? It's 0, right? Because because we clearly see that it's looking into the drain of two transistors. If we neglect channel length modulation, looking into the drain of the transistor, we get infinite impedance, so which means R out is infinite, right? But that is a trivial solution, and as we have emphasized multiple times in this course, you can neglect a high value with respect to, you can neglect a low value with respect to a high value, right? But you cannot neglect anything with respect to 0 or with respect to infinity, right? So essentially, or rather, let me rephrase, you cannot neglect anything with respect to 0, and if something is finite and your model is telling you it's going to be infinite, then which means the model is making an infinite percent error, right? So we should be mindful of these things while making approximations, right? So neglecting channel length modulation is an approximation, but that approximation holds under certain circumstances where there is a separate smaller amount of load connected to the transistor, right? But if there is no small load connected to the transistor, we cannot neglect channel length modulation. Okay, which means we'll have to put back the resistances. Let's assume M1 and M2 are the symbols M1 and M2 represents the transconductance of the transistor, right? So that's what we have been doing throughout. When I put the symbol, let's assume it means the transconductance, and if we have to incorporate channel length modulation, we will incorporate them as separate resistors, incremental resistors attached to them. Okay, so this is R1, this is R2, right? Similarly, we'll have R4 and R3. Okay, so now we are trying to figure out what is I test in terms of V test. Okay, so let's again let's break the problem down into multiple parts, because this seems like a messy way of going about uh, analyzing all four transistors together, right? So just like in previous cases, we would like to break this problem into multiple parts. What we would like to do is we recognize the fact that there will be an incremental current flowing into the drain of M2. Let's call this I2. And we also recognize that there will be some current flowing into the drain of M4. Let's call this I4, right? So we also, which means that we know that I test is equal to I2 plus I4, and we would like to figure out what is I2 and I4 in terms of I test and V test, right? So if we can do that, then essentially our job is done, right? So let's do the I2 first, because that seems familiar. We have done this in a separate context, right? So what should we do in order to figure out I2? So we break the circuit again into sub parts, right? So let's break it down into sub parts. Right. So when you are doing I2, let's not bother about I4. Okay, fine. So let's only concentrate on I2. So when we in the previous examples, when we were trying to find out the output impedance of a differential amplifier, how did we approach this? We approach this from the point of view of, we understand this M2 is the drain of the source of the M2 is not grounded, but it is loaded with something, right? It is loaded with some equivalent resistance, right? It is loaded with some equivalent resistance. What is the equivalent resistance? That equivalent resistance is the resistance looking into the source of M1, right? So this is R equivalent that we are trying to figure. If we know R equivalent, then we are all good, right? So in the earlier examples that we did, while trying to find out R equivalent, we saw that this node was rounded, right? But in this case, we see that the drain of M1 is not grounded, right? So we'll have to then we have to figure out what is this resistance looking up again is, right? So let's call this R equivalent to, right? So what will be R equivalent to? So clearly this is M3 is a diode connected transistor. So R equivalent to is 1 over GM3 plus GDS3, right? And you can, as we have talked about multiple times, we can neglect GDS with respect to GM. So this is approximately equal to 1 over GM3, right? So let's put our blocks back. So this becomes 1 over GM3, right? So now what is R equivalent to? So what is the impedance looking into the source of this M1? So again, how will you figure this out? We can actually write out what I would request you to do is to do this. Take this structure, take this structure and find out the impedance looking into the source of the MOSFET, right, in the presence of 1 over GM3. Okay, so you will see that so this is, I request you to do it yourself, right? So find out So DIY, find R equivalent to. So what you will see that after you find R equivalent to, under these conditions, you will see that R equivalent to can be approximated as 1 by GM1. This is almost similar to the case where I am neglecting that R1 is present or even 1 by GM3 is present, right? So once you do that, I mean this should make sense because we are looking into the source of the transistor, right? If I excite the source of the transistor, then GM times that current will flow through the transistor, which means I should be expecting resistances of the order of 1 over GM3, right? Right. So once you do the math, you will see that this approximation will hold good. Okay, fine. So if looking into the source of looking into this this node, if it's 1 over GM1, right? So where does it lead us to? It essentially leads us to this place where this node, this equivalent impedance becomes 1 over GM1, right? And we are trying to figure out what is the impedance looking down, right? So let's say R out 1, this is M2, right? So this is familiar territory. We have solved for this multiple times before. So what is R out 1? R out 1 is equal to twice of R1, since GM1 is equal to GM2, right? Okay, fine. So this solves for R out 1, right? So let's go back and put this guy. I copy this guy again. Okay, so if R out 1 is, or rather I should have said R out 2, right? Let's say R out 2 because everything was suffixed to 2. This is R out 2, right? So if R out 2 is twice of R2, right? Twice of R2. If R out 2 is twice of R2, then what do you think I2 is? So I2 becomes V test over twice of R2. Make sense, right? So if this I2 is flowing into the drain of M2, this I2 has to come out of the source of M2. It cannot go anywhere else, right? So this has to be I2. So again, if this I2 is flowing into the source of M1, it has to come out from the other side. It cannot go anywhere else. So that is also I2, right? So if this I2 flows into this diode connected configuration of M3, it will generate some voltage at the gate of M3. What will that voltage be? This voltage will be I2 by GM3 plus GDS3, which I can again say is approximately equal to I2 by GM3, correct? So if it generates this voltage of I2 by GM3, how much current do you think will flow through M4 and in which direction? So let me split this part up into multiple right? So what I am essentially saying is this voltage is how much? This voltage is let's say this voltage is Vx. If that voltage is Vx, what is the incremental current through M4? The incremental current through M4 is, in this case, Gm times Vx, because source is grounded. What is the direction? Going up, because that's what we have been using to characterize our P MOSFETs, right? So the current direction will be up. This will be Gm4 times Vx. So what is Gm4 times Vx? What is Vx? Vx is I2 over Gm3. And what is Gm3 and Gm4, relation between Gm3 and Gm4? Gm3 is exactly equal to Gm4 because quiescent current through M3 and M4 are identical, and so on and so forth, right? So this becomes equal to I2, right? So note that the I2 circulates back and it gets mirrored into the right branch and it flows on top also, right? Okay, what is the current through this resistance? That was R4, right? So this current is P test over R4, right? So that in what is I4? I4 is I2 plus P test over R4, correct? So what is then I test? I test is I2 plus I4. What is I2? I2 is V test by twice R2 plus what is I4? I4 is again I2, which is V test over twice R2 plus V test over R4, which is V test times 1 by R2 plus 1 by R4, correct? So which implies, what is V test over I test? It implies this is equivalent to R2 parallel R4, right? So essentially you see that we end up with a pretty similar expression that we had earlier, but the reason it's similar is a slightly bit convoluted, right? So eventually it seems like the output impedance of a differential amplifier with a current mirror load is only dependent, it seems like it's a parallel combination of the two transistors M2 and M4. That's all it seems like. But the reason it appears to be parallel combination of R2 and R4 is slightly more profound, because this happens because, as you see, there is a path, extra path that creates current mirroring and so on and so forth, right? But eventually the result is quite simplified. Eventually the result is almost like a common source amplifier with an active load, right? If you have a common source amplifier with an active load, then the output resistance is the parallel combination of the main transistor and the load transistor, and that's what this seems like. So one good thing is that this is easy to remember, right? So so eventually what becomes the Norton equivalent of a differential amplifier with a current mirror load? The Norton equivalent effectively becomes this, right? So let me also sketch the full thing now. So the incremental Norton equivalent of this becomes Gm times delta V, and R out becomes R02 parallel R04, or rather I should say RDS2 parallel RDS4, and incrementally this becomes the output voltage, right? So the another popular way of expressing the same thing is this. We know that this is a voltage control current source. What is What does this voltage control current source depend on? It depends on the voltages V1 and V2, and this is a transconductance of value Gm. This current is Gm times V1 minus V2, and we have a resistance here of R2 parallel R4. What is this Gm? This Gm is exactly equal to Gm of M1. Note that in the previous case where we didn't have a current mirror load, this Gm was equivalent to the Gm of M1 divided by 2. But in this case, it is equivalent to the Gm of a single transistor. Right? So again, this is plus minus, and I should sketch it in a more relevant manner. So this is V1, this is V2, and this is Gm times delta V only if V1 is plus delta V by 2 and V2 is minus delta V by 2, right? So this should ideally be Gm times V1 minus V2, right?